Good morning, dear students. I am Dr. Srinivas Badani, Professor of Chemistry in St. Peter's Engineering College. Today, I am going to discuss the splitting of d orbitals in square planar geometry. Splitting of d orbitals in square planar geometry. And applications. Applications of crystal field theory. Today we are going to discuss about these two things. Okay. Before going to that, in the last video, what we have discussed, what did I explain in that one? So I explained the splitting of d orbitals in tetrahedral complex and octahedral complex, and postulates and common splitting in d orbitals. So we have know in that splitting nature, easy level, two sets are there, easy set and 2 digit. One is the lower energy and another one is the higher energy. Axial orbitals, non-axial orbitals. Okay, these are we discussed in the last video. The octahedral and tetrahedral are quietly opposite in nature. The splitting nature is quietly opposite. You have to remember that thing in yesterday video or last video. Okay, today we have to discuss the splitting of d orbitals in square planar geometry. Square planar. Can anybody draw the square planar? Square planar. Just square planar. Okay, no need. Square planar means plane like this. This is the square planar. Okay, this is about the square planar structure. So here little bit is different. Okay, so before going to discuss about the square planar, we have to know the energy level diagram. That is most important. If you know the energy level diagram, then splitting pattern is very easy to understand. So what is that? The energy level diagram means increasing order of the energy level diagram. This is the energy level diagram. Here same thing, 5d orbitals. How many? 5d orbitals, dxy, dyz and dzx. dx square minus 5 square and dz square. 1, 2, 3, 4, 5. dxy, dxz and dyz. dxz and dxy. dxy, dyz. And dx square minus y square and dz square. So these are the 5 degenerate orbitals in free metal ion, central metal ion, free metal ion in central. This is the planar. Okay, free metal ion. So here same thing, energy raised up. One, 2, 3, 4 and 5. So this is the average energy. Average energy in spherical crystal field. Crystal average in spherical crystal field. Average of d orbitals. And here they split into two sets, EG set and 2TG set. And EG set. And then again here two tabs are three. So in 2DZ dxy, dxz and dyz. Here dx square minus y square and dz square. Here again this is splitting takes place. So this is the dxy, it's the dz square, dx square minus y square, and the dxj and dy z. This is the splitting pattern of the square planar diagram, square planar structure. Square planar. So this is the tetrahedral. We know that easy and tetrahedral and octahedral. Both. One is opposite. So EG and TDG. Tetrahedral and octahedral. Just now the square planar is like this. So the energy here when the ligands approaches to the central metal ion, they are raised up in the crystal field, spherical crystal field. Then here the splitting takes place into the dx square minus y square, dxy, dz square and dxz and dyz. Okay, now the main thing is here we have to know that one example, if is the splitting pattern of the square planar of d orbital diagram, we have to know that simple one example. If one example you have to know. So that is the D8 configuration. We have to see the D8 configurations. If the central metal ion, this is the central metal ion, has a D8 configurations. For example, D8 configuration. D8 configuration. D8 configuration is nothing but it is having the 8 electrons in this. 1, 2, 3, 4, 5, 6, 7, 8. This is called what? D8 configuration. D8 can be totally 8 electrons are present. 6 electrons will occupy the 3D level. 1, 2, 3, 4, 5, 6 and 2 electrons are in this one. Here also 1, 2, 3, 4, 5, 6, 7, 8. Okay. The D8 configurations, total number of 8 electrons, 6 are in 2G level and 2 are in EG level. 6 electrons will occupy the T2G orbitals and 2 electrons will occupy in EG orbitals. The single electron in dx square minus y square and single electron in dz square. So 2 single electrons are present in dz square and dx square. Here, very important, please listen carefully. The single electron in dx square minus y square orbital is being repelled by the 4 ligands. This is repelled by the how many ligands? 4 ligands. The single electrons in dx square minus y square is being repelled by the 4 ligands, whereas the dz square, single electron in dz square is being repelled by the 2 ligands. 2 ligands. This is important. What is that? The single electron in dx square minus y square orbital is being repelled by the 4 ligands, whereas the electron in the dz square orbital is being repelled by the 2 ligands. Thus the energy of dx square minus y square increase relative to that of dz square. This energy is increased. This energy is increased relative to that of dz square. Okay, that is the reason it is very helpful. If the ligand field is sufficiently strong, if the ligand field, 4 types are attacked. If the ligand field is sufficiently strong, the energy difference between these orbitals become larger than the energy required to pair electrons. The pairing of electrons, listen carefully, if the ligand field is sufficiently strong, the energy difference between these orbitals become larger than the energy required to pair the electrons. Okay, a stable arrangement arises when both the Eg electrons pair up and occupy the lower dz square. Here, these 2 electrons will come to here. A stable arrangement arises here. The Eg electron pair up and occupy the lower dz square, which x square minus y square orbital empty. This is empty orbitals. This is empty orbitals. That is most important. Once again listen, here this is occupied the 4 ligands. This is the 2 ligands occupied the ligands. The energy of dx square minus y increases compared to the dz square. If it is sufficient, the ligand field is more strong, the energy difference between these orbitals, dx square minus y square and dz square orbitals, become larger than the energy required to pair the electrons. Larger than that. That is the reason a stable arrangement takes place. The Eg electrons pair up and empty is the dx square minus. Dx square minus orbital is empty. So this is most important, we have to describe the example. Okay, the ligand which approach along plus z and minus z directions. Here the z plus z directions and minus z direction. Always the ligand which approach along plus z direction and minus z directions meet strong repulsive force from the field dz square orbitals. Once again, what is that? The ligand which approach along plus z and minus z directions meet strong repulsive force from the field dz square orbitals. dz square orbitals. dz square orbitals. dz square orbitals. Thus only 4 ligands succeeded in bonding to the metal. Only 4 ligands. A square planar complex is formed. Here the only square. 1, 4 ligands. Mean this one dx square. Succeeded only 4 ligands. So remaining these 2 electrons is raised up the energy between the dxy, dxz and dyz. This is more energy level. Okay, they raised up the upside and containing the 2 electrons, and dxz containing the 2 electrons and dyz also 2 electrons. Okay, and best example is this is the best example, nickel tetracyanide. We can give the one example. What is the compound? Nickel tetracyanide. Nickel tetracyanide. This is the -2, this is the +2. Okay, nickel tetracyanide. Mean central metal ion is the nickel, and this is the cyanide minus cyanide minus cyanide. These are the ligands. Best example. This is the best example. Okay, once again, what is that? Today we have to discuss what? Splitting of d orbitals in square planar geometry. So what is that? In free ion containing the d8 configuration means 8 electrons are present in the d orbital. Whenever the ligands approaches to the central metal ion approaches to central ion and takes the average energy in spherical crystal field. This is the spherical crystal field, and splitting takes place Eg and 2Tg. So 2Tg containing the 6 electrons and Eg containing the 2 electrons. Again, this one is the dx square minus y is occupied by the surrounded by the 4 ligands here, the 2 ligands. So that is the reason the dz square taking the 2 electrons and pairing takes place. And dx square minus y is empty, and here the T2G orbitals again split into dxy, dz square and dxz. Here compared to these two, here the dxy is a more raising upper than the dz square orbitals. So this is about the description of the d orbitals in square planar geometry. Okay, now some applications. Can we look at some applications? What are the applications? Okay, we know that applications already. So already in introduction I will tell you. So the first applications. Many applications are there. But we will discuss the 2-3 applications today. Okay. So what are that? The one. Colors of transition metal complex. What are that? Colors of the metal transition complexes. Metal complexes. Colors of transition metal complexes. Most of the transition metal complexes colored. We know that most of the nickel tetracyanide, platinum tetracyanide, all our complexes compounds are, EDTA color. Already we completed in EDTA water lesson in the first unit. EDTA, it is also complex. Ethylene diamine tetra acetate. Ethylene diamine tetra. That is a ligand. It is a complex structure. Already we discussed it. There is a color property, blue color, mean that the EBT indicator we have used in that. Okay, mean most of the compounds are color property nature. The colors of these complexes is attributed to DD transition between T2G and EG. Between T2G and EG. So between T2G because the energy differences takes place. The energy difference, Eg orbitals and 2g orbitals. So why they are coloring of all the orbitals? Because the reason, what is the reason? Here the dd transition takes place between the Eg transition and Eg. For example, in tetrahedral complex and octahedral complex, the delta like the Tt 2 by 5 and 3 by 5 Eg orbital 3, and different energy status are there. In octahedral also same, in squareplanar. So that is the reason more color properties are there. Yellow color, pink color, different types of colors. Because the reason only that we studied in this one mean that splitting of the orbitals. The degenerate orbitals, when splitting takes place, like Eg orbitals are too visible, the color will come. That is depend upon the direction. Mean ligands are approaches to the metal ion. When the ligands are approaches towards the metal ion, the colors takes place. So this is about the color of the transition metal complexes. This is very important. The studying of colors, copper color, silver complex, like that, the different type of colors are there. Okay, next is the magnetic properties of complexes. What is that? Second one is the magnetic properties. Magnetic property of complexes. Magnetic properties of complexes. The magnetic moment helps in predicting the valence state of the metal ion in octahedral complex and nature of the bonding in the complex. What is that? That magnetic property mean diamagnetic, paramagnetic, ferromagnetic. So this magnetic moment helps in what? Predicting the valence state. Valence state mean that valence is how much? The plus 5 or plus 4, plus 6, plus like that different valences are there. That is the metal ion in octahedral complex and tetrahedral complex and any other complexes. The nature of the bonding in the complex. Nature of the bonding in the complex. So magnetic property and color property is very important in predicting that different types of molecules and shapes of the all transition metals. So based only the splitting of d orbitals, especially splitting of d orbitals only. If there is no splitting takes place in the d orbitals, there is no color formation, there is no magnetic properties. So all these things are not happened in that. So mainly depend on the split. That is the reason we studied the example only squareplanar, octahedral and tetrahedral structures we studied completely. Because the reason this is very important for the EEE student and EC student. Because many metals are present, wires, mean the complex nature, the color properties. So that is the reason these are the crystal fields are very important. And tomorrow we are going to discuss the semiconductors, that solids, the bandwidth and semiconductors, conductors and non-conductors. The things that this will help more in that one, because the valence electrons, valence band, the jumping of electrons, whatever may be, so that is more useful. Before going to discuss that one, so we have to know the splitting of the compounds, splitting of the d orbitals nature. Okay, so thank you very much.